Welcome back to week 9, and we are going to continue on and talk about how we use different techniques to date geologic events. And specifically, we're going to talk about numerical age. So some of the ways we can get an actual number date on events are using tree rings, lake layers or varves, ice cores, isotopic dating, and fission track dating. So with tree rings, we can basically count the tree rings in a tree stump, and if we have a series of layers and these layers have trees deposited in them or buried in them, we can actually count the tree rings in each of those different trees, and sometimes we can actually correlate different tree rings to one another, because if those trees were living at the same time, they're going to have very similar tree ring widths, because of environmental conditions control how thick those tree rings are going to be. So lake layers, in a lake environment we have every single winter and summer we have a winter layer and a summer layer being deposited. So we can actually count those over a series of deposits or cores that we can get. So these would be some cores that were collected from this lake environment. So sometimes these lake layers might have an ash layer in here that we can get a good radioisotope date to double check our counting. These lake layers can also trap pollen, so we can get an idea of what the environmental conditions were like, what type of trees and vegetation were growing in this area at that time. And ice cores are very similar. They have these layers every year. We can also see the if there's any ash layers that are dust layers, and we can get some isotopic dates off of those. So using isotopes to date different events, we can actually use these unstable isotopes, what we call a parent that's going to be decaying to a daughter atom. So over time, each of these different unstable parents, through this process of radioactive decay, this happens in a set interval. This decay happens every X number of years over time. So the parent is what we start with, and then the daughter is what we end up with. And this decay process can happen in a variety of different ways. The three main types are alpha decay, where the unstable parent emits an alpha particle, 2 protons, 2 neutrons, and then in beta decay, we emit an electron, and then in electron capture, the unstable parent captures an electron to become more stable. So when we look at this decay process over time, we can take samples and actually record this and measure and monitor some unstable parents and measure how much of what is left over. So basically we know these half-lives based on samples that we've taken and experiments that we have done in the lab. So we've been able to repeat this experiment over and over and over and over again to be able to get this kind of results. So basically we start out with 100% of that unstable parent. When you have 50% of that parent has changed to a daughter, that's 1 half-life. So when it takes for the amount of time it takes for this parent to become half-daughter. So 50-50. When another half-life goes by, we take that parent, so we're left with 50% of the parent. Half-life goes by, that 50% parent is then cut in half. Half of it decays, and so we are left with 25% of the parent, 75% of the daughter. Third half-life goes by, and that 25% parent gets cut in half, splits in half, and we have 12.5% parent, 87.5% daughter. So when we look at this stuff in the lab, we're measuring, using some high-tech equipment, how much of each atom there is. And then when we get that ratio, when we can determine, depending on what isotope we're looking at, we can determine, okay, we know 6 half-lives have gone by, and each half-life is X number of years, so the sample is this many years old. So some of the common isotopes that are used, you can see here uranium, rubidium, potassium, and carbon. So these are the main types that are used. So with carbon-14, it has a pretty short half-life, so that's good for dating more recent events. When you want to date something that's happened a long time ago, say the formation of the Earth, we want something with a much longer half-life. Something like uranium-238 or rubidium-87 would be two good methods of dating. Or maybe even thorium-232 would be a good one, because these have very, very large half-lives. So the reason for that is if we use something that has a shorter half-life and maybe 15 half-lives has gone by, we're looking at really, really small fractions of parent to daughter. Very, very hard to pick up. Whereas if we have a longer half-life, then we can, it's a little more easy to say maybe 2 half-lives went by, or maybe 1 half-life went by. It's much easier to count the atoms and molecules for those. So, and these are kind of what we use to date major events and rock units and rock layers. So basically, when, say we have a mineral that cooled in a igneous intrusion, as soon as that mineral cooled, that mineral is then isolated, and the radioactive isotopes in that mineral start to decay, and then the parent and daughter are trapped in that mineral. So then we can measure, taking that mineral, we can measure how many of which are in there and determine how many half-lives have gone by. We can also use what's called fission track dating. Basically, this is counting how many of these little damaged trails in a mineral are left behind from uranium-bearing minerals that are decaying and emitting high-velocity particles. And as that high-velocity particle is emitted, it's basically breaking the structure of the mineral. And you can see it's kind of bouncing its way through and creating a pathway. And we know this rate, so as we count those fission tracks in a mineral, we can get an approximate date. So that's kind of radioactive or absolute dating in a nutshell. Please check your textbook out for details. I will see you in lab.